Hello and welcome to this class brought to you courtesy of O3 Schools Jamb app, one of the very best apps for learning for your Jamb. You have a wide array of activities included in the app and features designed to help you as you prepare to take your Jamb. So, O3 Schools Jamb app, on getting your app, you have to activate it to gain access to these features, and the activation key simply costs 2,500 naira. 2,500 naira only. Simply follow the steps on the app and you shall be able to activate your app and then enjoy the full features. And with that, let's get off to the races. In this class, we shall be studying the phenomenon of radioactivity. Radioactivity. Now, radioactivity was discovered by Marie Curie in the year 1898. But what is radioactivity itself? Radioactivity refers to the spontaneous emission of particles and rays from the nucleus of an atom. Now, when we say spontaneous, I mean it is continuous and it is unaffected by environmental factors. You don't have to do anything to make this radioactivity start. You don't really have to do anything either to make it stop. It's just part of the nature of particular atoms. And any atom that is capable of the phenomenon of radioactivity is said to be a radioactive atom or a radioactive element. So elements which undergo radioactivity are radioactive elements. And these particles and rays being given out are of three specific types. We have the alpha particles. Alpha particles are represented with that symbol. We have the beta particles. And then we have gamma rays. And please, this is not a mistake of language. Your gamma is not a particle. It is simply an electromagnetic wave. So it is gamma rays, alpha particles, and beta particles. Now, naturally, these particles or rays, they move and behave in different manners dependent on their own intrinsic property. For example, your alpha particle is represented by helium atom. Your beta particle is simply a high energy electron, while your gamma ray, like we said, is simply an electromagnetic wave. And as such, this alone is enough to define various differences in their behavior. For example, alpha particles have large mass, at least compared to the others. Beta has average mass, and gamma has no mass whatsoever because it is simply a wave. Now, also, based on these masses, that tells you that this guy will move at the least speed, and this is the fastest speed. Based on being an electromagnetic wave, it moves at the speed of light, which is c, or as you should be aware, c is 3 times 10⁸ meters per second. Beta particles move at average speed, somewhere between the regions of 95 to 97% the speed of light, while these guys move at around 5% the speed of light. As you can see, the more massive ones move slower than those with no mass. Added to this mass, you now also have penetration power. Your gamma rays having no particle, and it's easy to penetrate. So they have the highest penetrating power, and you can only stop them using a thick block of lead. Your beta particles have average penetrating power, and you can stop them using sheets of aluminium. While last but not least, your alpha particles have the least penetrating power and can simply be stopped with sheets of paper. See, so these are different properties, but one very important property refers to their behavior under the influence of electric and magnetic fields. Say, for example, this is an electric field. here is minus, and here is plus. How can I define these three types of rays that came out? Now, your alpha particles are positively charged, and as a result, they get attracted to the negative side in an electric field. So the one going to the negative must be alpha. Your beta particles are negatively charged, and as such will be attracted to the positive, which means this must be beta, while your gamma particles have no charge whatsoever, and as a result, they are unaffected by either electric or magnetic fields. You see, these are various properties which these particles contain. Once this is clear, the next one must then look at is a phenomenon referred to as half-life. Half-life. Now, what is half-life? Half-life refers to the time taken for half of a radioactive sample to decay. That means if I have radioactive sample, say of 100 grams, and we know this thing is constantly giving out particles. At a certain point in time in its life, after giving out a certain amount of particles, this thing must go from 100 gram and now become 50 gram, which is half of the initial amount. The time taken for it to become half of that amount is referred to as half-life. And one of the special behavior of radioactivity is that half-life is constant no matter the size. That means it will also take the same half-life to go from 50 to 25, and also the same half-life to go from 25 to 12.5. It doesn't matter that in this case it is losing a smaller amount. In radioactivity, half-life is constant no matter the change in mass, as long as you are noticing that half-life is the time taken for half of whatever was there before to decay. Which means if you have a sample like this that's removing, then the number of times it has decayed, will be the total time that has passed, represented by small letter t, over the half-life, which is represented by t half. Therefore, number of decompositions will be time over half-life. That's one. Next up, we also have to analyze the behavior in terms of what will be left. Say I start with an initial amount NO. After certain number of half-lives, I will be left with a new amount N. This is the amount remaining. And with a bit of common sense, I know that if I start with NO and I have N remaining, then the amount that would have decayed will be the amount I started with NO minus the amount that is left. And to calculate for this amount that is left, we have a simple formula, which is that N over NO equals 1 over 2 raised to power N. See? And that is the simple calculation for half-life. However, there's another value referred to as decay constant. Decay constant basically tells you how much is decaying per second. And in that case, you should know that your half-life equals to 0.693 over the decay constant. So these are some of our most important formulas in the theory of radioactivity. Now, moving on from this, next we shall then look at our nuclear reactions. Now, nuclear reactions are radioactivity because in a typical chemical reaction, the reaction is undergone by the valence electrons, the electrons on the outermost shell. But in radioactivity or nuclear reactions, these reactions are taking place within the nucleus of the atom itself. And in that case, the behavior is special. Nuclear reactions are of two types. There is nuclear fusion and there is nuclear fission. As the name implies, nuclear fusion means to join together, while nuclear fission is to break. Nuclear fission means to take two smaller elements and combine them under very high temperature to form a much heavier element and the release of energy. While on the other hand, nuclear fission refers to taking a single element and breaking it down into smaller elements, also accompanied by the release of vast amounts of energy. So that's nuclear fusion and nuclear fission. On Earth, we have several nuclear power plants, and all nuclear power plants on Earth, though, run on nuclear fission. These plants run on fission because it is much easier to break down than to create. The temperature required for nuclear fission is so high that we don't yet have any earthly materials that can withstand that temperature. For an example of nuclear fission, is undergone within the sun. In the sun, hydrogen atoms combine under high temperature to produce helium atoms. So that is the basics of radioactivity. And also, based on the fact that these reactions occur within the nucleus, that tells us one more thing, which is that as these reactions occur, our elements actually change fundamentally from what they were before into new elements. Say, for example, I was to have a certain element, atomic number 32 and mass number 232. And just in case we've forgotten, atomic number is the number of protons, and mass number is the number of protons plus the number of neutrons. If this element was to break down in nuclear fission and produce maybe a new element, let's call it 36 and 102, plus another element which we do not know, accompanied by the release of, let's say, two alpha particles. In this case, what must I observe about this reaction? Number one thing is that these elements have changed drastically. This will no longer give me input 92. Instead, I look here, 92. I know that all the atomic numbers here must add together to give me 92. So that means 92 equals to 36 plus just call the n. Then here will be 2 times 2 because there are two helium atoms, and that is 4. So 92 equals to 36 plus 4, which is 40 plus n. And therefore n equals to 92 minus 40, which is 52. So you see, the new atomic number of this element here must be 52. And the same thing happens with the mass number. 232 will be 102 plus, let's call that number A. Then 2 times 4 is 8. So 232 will be 110 plus A. A equals to 232 minus 110, which is 122. So you see, this will be the breakdown. So in simple questions like this, when you are simply given a reaction, simply know that you have to either subtract or add away from whatever it is given out to give you the new elements that are produced. And on that note, I think it is time for us to once again open our O3 Schools Jamb apps on our phones or laptops so that we can actually solve some questions from this topic. So, opening our app, we shall see that we have several questions in this area. Our first question, however, shall be from the year 2010, question number 46. The radioisotope 23592 uranium, 23592 uranium decays by emitting two alpha particles, three beta particles, and a gamma ray plus one gamma ray. And then, what is the mass and atomic numbers of the resulting daughter element? Now I can present the mass number with M and the atomic number with A. Now, because we're told to ask what is the mass and atomic number, it means that my first answer must represent the mass number, while the second represents the atomic number. So, as we did in the explanations, all we simply have to do when dealing with the mass number, take a look up here. That will be 235 equals to, my mass number, 4 times 2 is 8, 3 times 0 is 0, gamma is a ray, it does nothing, so m. So that'll give me that 235 equals to 8 plus m. Collect items, m equals to 235 minus 8, and that is 227. So getting that, I should already know that my answer must be option C. Because if the mass number is coming first, then the only way for the answer to be correct is to be 227 and 91. However, let's just prove it. Taking a look now at the bottom, that will be 92 equals 2 times 2 is 4. 3 times minus 1 is minus 3. Gamma does nothing as usual. Then A. 92 equals to 4 minus 3 is 1 plus A. A equals to 92 minus 1, which is 91. So you see, this new element shall have atomic number of 91 and the mass number of 227. And that is that for our very first question. So you see, very simple steps. Next, let's take a look at the year 2001 on a very similar question. Year 2001, question number 45. In this case, we are told the particle emitted when 3919 potassium decays to 3919 potassium is what? Think about it. What can this element give out such that it remains exactly the same? If it's a helium atom, both mass and atomic number will change. If it's a beta particle, the mass number remains the same, but the atomic number changes. However, if it gives out a gamma ray, which is basically nothing but the electromagnetic wave, everything remains the same, implying that the only thing it can give out to have no change must be a gamma ray. And you see, our answer is therefore option D. Gamma ray causes no change in the structure of the elements. All right. Question number 3. This one comes from the year 2005, question number 44. 2005, question 44. The time it will take a certain radioactive material with a half-life of 50 days, the half-life is 50 days, to reduce to 1 over 32 of its original number. That means what is left right now is 1 over 32 of the original number. Or in other words, n over n naught equals to 1 over 32. We have to find the time it will take. Now this is quite simple. All you have to do first of all is remember that the formula for n over n naught is 1 over 2 raised to power n. Notice my left hand sides are the same. Therefore, I can equate the right hand sides. 1 over 32, 1 over 2 raised to power n. Take both sides upwards. That will give me that 2 raised to power n equals 32. Now, how do I analyze this quite easily? All I have to remember is I cannot express 32 in terms of 2 to any power. And my obvious answer is yes. 32 is 2 raised to power 5, 2 in 5 places. And therefore, my n must be 5. That means for it to have 1 over 32 remaining, it must have decayed 5 times. And with a tiny bit of logic, if to decay once takes you 50 years and it decayed 5 times, how long must that have taken? It must have taken 5 times 50 years, which is 250 years. or days rather, sorry, our question is in days, and so our answer must be option C. So you see, very, very simple steps. All right, and our question number 4 is from the year 2002. Question number 43. 2002, number 43 from your Jamb app. This one says, the percentage of the original nuclei of a sample of radioactive substance left after 5 half-lives is. Basically, we have been asked what percentage of any sample will be left after 5 half-lives. To analyze, you can try using the common sense method, like I prefer to call it at times, and say I start with 1. After 1 half-life, half is gone, and I will have half left. After my second half-life, I lose half of this half, and I have 1/4 left. That's 2 half-lives. After the third half-life, half of that again, 1/8. The fourth half-life, 1/16. And the fifth half-life, 1/32. And however, they're asking us to find it in terms of percentage. What is the percentage? To simply find the percentage, is simply to multiply by 100. So using your calculator, 100 divided by 32 is 3%. Or to be exact, 3.125. But since our option doesn't have decimal point, we are taking 3%, which is option C. You see, very, very simple. In fact, let's try that question. This one from the year 2000, question number 37. 2000, number 37. This one says, if the fraction of the atoms of a radioactive material left after 120 years is 1/64, the fraction left after 120 years, 120 years has passed, and we now have a fraction n/no as 1/64. What's the half-life of the material? Now I simply have to remember exactly what I did over here, and that n/n0 is 1/2 raised power n. So I have to equate my right hand sides. 1/2 to the power n equals to 1/64. And that means, so that's 64, not 16. 2 raised power n must be 64. Can I express 64 as a power of 2? Yes, that is 2 raised power 6, implying that n must be 6. Therefore, if I have decayed 6 times in 120 years, how long does it take to decay once? That will be my total time over number of decompositions. 120/6 means my half-life must be 20 years. See? Quite simple. Moving on, let's try a new question. This one from the year 1995. Question number 39. 95, question 39. For this one, we are told that the half-life of radioactive element is 9 days. Half-life is 9 days. What fraction of atoms would have decayed in 36 days? So, half-life is 9 days, but 36 days has passed. So many times we notice it has decayed. That will be total time over half-life. 36/9, which is 4. And therefore, that means I'm decaying 4 times. Let's get the fraction. If I start with 1, I'm using common sense method again. It's faster occasionally. Start with 1. After 1 half-life, that's half. 2 half-lives, 1/4. 3 half-lives, 1/8. And 4 half-lives must be 1/16. See? Quite straightforward. Our answer is option A. Alright. Let's take one last question. This one is from the year 1998. Question number 48. Year 98, question 48. For this one, we have been told a radioactive substance has a half-life of 80 days. The half-life is 80 days. If the initial number of atoms in the sample initial number is 6 times 10 raised power 10, how many atoms would remain at the end of 320 days? It decays once every 80 days, and now 320 days has passed. How many times will it have decayed? That will be 320 over 80, which means 4. It has decayed 4 times. And based on that knowledge, we want to then determine what number of atoms would be remaining. And one more time, it's simple. N over N naught equals 1 over 2 to the power of N. We do not know what N is, but N naught is 6 times 10 to the power of 10. So 1 over 2, and small n is 4. So n over 6 times 10 power 10 will be 1 over 2 raised to the power 4 is 16. So to determine the value of n, I simply have to cross multiply such that n will be 6 times 10 raised to the power 10 over 16. And again, remember, we don't have a scientific calculator. So what do? Simply do 6 divided by 16, which will give you 0.375 times 10 raised to the power 10. And then when you put this in index form, you get 3.75 times 10 raised to the power 9. And therefore, my answer is option A. And on that note, we've come to an end of this class. Please like and subscribe to see more videos on several other topics and even different subjects. And remember, this is all brought to you courtesy of O3 Schools Jamb app. Thank you for watching. My name is Athanasius.